Okay, lesson number 7, double angle identities. So yesterday we looked at sum and difference identities. We're going to use the sum identities to help us do double angle identities. So it says, consider the statement sine 2a equals 2 sine a. Determine whether or not we can verify this statement if a is equal to pi over 6. So, if I look at the left-hand side, I have sine 2 times pi over 6. And what is 2 times pi over 6? Pi over 6, which equals pi over 3. So this equals sine pi over 3. And what is sine pi over 3?
0.8.
3 over 2.
Are we supposed to have those memorized?
No, you don't have to have them memorized, but you probably see 0.8660 enough to realize that it's root 3 over 2. Okay? But if you can't remember it, we can always take that answer, square it on the calculator, get 3/4, and then square root it to go back. Okay? So that's the left-hand side. So the right-hand side says this is supposed to be equal to 2 times sine pi over 6. So what is pi over 6? One half. And what's 2 times 1/2? 1. Are the two sides equal?
No.
So what can we say about this statement? Is this statement true or false? It's false. So there is an identity for sine 2a. And to find that identity, what we're going to do is we're going to use the sum identity for a plus b. Because instead of going a plus b, we can go a plus a. Because if I take a and I add it to a, how many a's do I have? 2. So sine a plus a is the same as sine 2a. So if we look at sine a plus a instead of a plus b, and we use the identity that's been nicely written up at the top, it means that instead of being sine a cos b, it's now cos a, and cos a sine b. So what I get is sine a cos a plus cos a sine b. Or sorry, not b, sine a. Oh, cos a sine a can be written as sine a cos a. And how many sine a and cos a's do I have?
2.
2. So this becomes 2 sine a cos a. So all we've done to get this double angle identity is we've used the sum identity. So let's do the same thing for cos 2a. So cos 2a would be cos a plus a. So if we look up at the top, cos a plus b gives me cos a cos b. So this time it would be cos a cos a minus sine a sine a. So if I take cos a and I multiply it by cos a, what do I get?
Cos a squared.
Cos squared a. It's fine to say cos a squared, Rachel, as long as you mean it like that and not like that. Okay, it's the whole thing that's being squared. That's why we tend to put the squared with the cos. And then if I take sine a and multiply it by sine a, I would get sine squared A. Okay? And now we're going to do the same thing for tan 2A. So tan 2A would be tan A plus A, which would be tan A plus tan A. And then on the bottom would be 1 minus tan A, tan A. So if I take tan A and I add it to itself, what do I have? 2 tan A. And if I take tan A and I multiply it by itself, so I've just developed 3 more identities, which again are on that formula sheet for you to refer to. It is beneficial to know how we derive these 3 identities, but you're not required to memorize them. Okay? Now, this one right here has a little bit of a contingency, because in this spot right here, I can go back to my Pythagorean identity, which says cos squared A plus sine squared A equals 1. And then I could rewrite that around. So I could have cos squared A equals 1 minus sine squared A, which if I put in here, I get 1 minus sine squared A minus sine squared A, which gives me 1 minus 2 sine squared A. So this 1 minus 2 sine squared A is also equal to cos 2A, just by rearranging and doing another substitution. If I isolate for sine squared A and get 1 minus cos squared A, I get cos squared A minus 1 minus cos squared A. The 2 minuses give me a plus, and I get 2 cos squared A minus 1. So if you flip onto the next page, that's outlined on the next page. Now your formula sheet actually gives you all 3 versions of cos 2A, which again is something new because they never used to give you these 2. It was kind of like the Pythagorean identity. You had to kind of know that they could be there. Now they're given to you. So it says the proof for the other 2 forms as it asked for in assignment question number 1. We just did that, just by taking the Pythagorean identity. So it says prove that the identity 2 tan x over 1 plus tan squared x is equal to sine 2x. Prove that the identity is valid and state the non-permissible values. So remember, when we do a proof, we do the left-hand side and the right-hand side. Okay? So if I look at the left-hand side, 2 tan x over 1 plus tan squared x. If you look on your formula sheet, what do you think you can do with that left-hand side of the equation? What can I do with tan x? Okay, so let's start with that. 2 sine x over cos x. about the bottom, the 1 plus tan squared x? Can I do anything with that? Do you see a tan squared x or tan squared theta anywhere on your formula sheet?
You can change it to secant squared.
What do I know about secant?
It's the inverse of cos.
It's the inverse of cos. So secant is 1 over cos squared x. And then to divide fractions, I multiply by the inverse. So when I multiply by the inverse, the cos x in the denominator is going to cancel out one of these cos x in the numerator. And I get 2 sine x cos x. Is there anything else I can do?
Doesn't that equal sine 2x?
So it equals the right-hand side. So remember, if we go back to those hints of doing proofs, the biggest hint, which tends to be one of the more useful ones, is as much as possible, try to change things into sine and cos. So that because they tend to be the more common identities that you see throughout. But look for things like a Pythagorean identity. Anytime you have a 1 and something squared, look to see if it's part of those Pythagorean, because we have the sine squared plus cos squared equals 1. We have the 1 plus tan equals secant, and the other one was 1
Plus cotangent equals.
cosecant, right? So 1 plus cotangent squared equals cosecant squared. So whenever you see those 1s and those squares, or 2 squares being added or subtracted, check to see if it's a Pythagorean identity. Because if I can rewrite this as secant, I can then write it as 1 over cos. And now I have only basically 2 variables, so to speak. Whereas here I have 3. Okay? So now if I look at my non-permissible values, we look for denominators. So if we look right here, I have my first denominator, cos x. So my non-permissible value would be that cos x cannot be equal to 0. And if I think back to my diagram or my picture of cos x, it's 0 at the pi over 2 and then multiples of that. So x cannot be equal to pi over 2 plus multiples of pi x. So every pi radians after that. Okay. With my secant squared x being 1 over cos squared, again we get that denominator that can't be equal to 0, so we've already taken care of that. If tan squared x were to equal -1, I would have a 0, but tan squared is never going to be a negative, because I'm squaring it, so it's always going to be a positive value. So I don't have to worry about this denominator. So I've taken care of my non-permissible values. Okay. So class example number 2 says use the identity sine 2a equals 2 sine a cos a, with a being replaced by 3x to determine a double angle identity for sine 6x. So what that means is I can say that sine 6x is the same as sine 2 times 3x. And sine 2x is 2 sine 3x cos 3x. So sine 2a is 2 sine a cos a, but my a's this time are 3x. So if we do the same thing for cos 10a, I can write cos 10a as cos 2 times what? 5a. And what is cos 2a equal to?
Cos squared a minus sin squared a.
So cos squared a minus sine squared a. So cos squared a is now 5a. And then sine squared 5a. Hold on. Did you take the worksheet for this? The one that we were working on in class today?
Yeah, I thought.
Okay, perfect. Thanks, Alicia. Okay, what about tan x? How can I write tan x as tan 2 times something?
Mrs. Goodall.
Yes.
For b, like, because cos 2a is equal to like 3 different ones, so how do you know which one to use?
Always pick the first one. So always start with the first one. The only time you would use the other two is if you were in an identity and you were trying to use it to simplify to something further.
Okay.
Okay? Okay, so tan x. How do I get x if I have to multiply it by 2? 2 times what? X over 2. Or a 1/2 x, the same as x over 2. So according to my formula, what is tan 2a equal to?
2 tan a over 1 minus tan squared.
So a is now 1/2 x over 1 minus tan squared 1/2 x. Okay, class example number 3. Express each of the following in terms of a single trig ratio. So if I have 2 times sine 4x cos 4x, what is this equal to? Sine 2a, which is 4x. And what's 2 times 4x?
8x.
So I get sine 8x. Okay, what about cos squared 1/2 a minus sine squared 1/2 a?
Cos 2a.
So cos 2a. Well, what's a equal to?
1/2
And what is 2 times 1/2 a? So this would be equal to cos a. Okay, the last one. Sine 5/2 x cos 5/2 x. What does that look like? What is it missing?
The 2.
It's missing the 2. So I can't just stick a 2 in there because it changes the value. although it would be nice to put a 2 in there because then I get a 2a. So what can I do to counterbalance putting the 2 in there? Divide by 2. So the same as multiplying by 1/2. So if I was to put it that way, can I now work from here? Because the 2 times 1/2 has not changed the value of the equation, but this inside my brackets now becomes sine 2a. So sine 2 times 5/2 x with the 1/2 still out in front. And what is 2 times 5/2 x?
Five.
5x. And the 1/2 still stays out in front. So I get 1/2 sine 5x. So we have question 2b.